In the next video, we're going to worry about changes in state with evaporation and vapor pressure, boiling and boiling point, and sublimation and melting. We touched on it a little bit in the last video. We're going to go a little bit more in this one. Okay, before we go any farther, there's a couple things that I left out of the last couple videos. You are going to need to know bars and inches and kilopascals and psi, which is pounds per square inch, and that atmosphere is the smallest of all of them as far as 1 atmosphere equals 760 torr. So 1 atmosphere equals all of these things. So 29.9 inches mercury is equal to 101 kilopascals is equal to 1.01 bar, or 14.7 psi, and of course 760 millimeters mercury or torr. You need to be able to go back and forth between that. And so to do that, you just say I was given, for instance, 77 atmospheres, and I wanted to get to kilopascals. So I would use the things I've got up here, and for every 1 atmosphere I would get 101 kilopascals. Then I could cross out atmospheres. I could take my calculator and times through here, and I would get 7,777 kilopascal, or basically to 2 sig figs, 7,800 kilopascals, or kPas. So you need to be able to go back and forth between any of them. You also need to be able to use Pervnert and plug in for the different parts of that, and any of the combined gas laws, Charles, Gay-Lussac's, Avogadro's, any of those, you need to be able to just plug in. Given what you have, figure out what you don't have. So make sure that you're able to do that. We're going to be doing some worksheets in class. There's also many examples around page 180 to 182 in your book. So look at those. Be able to do Dalton's and Graham's law and just plug in. Okay, because if you know the laws, all you have to do is plug in to find the answers. Okay, so this is our phase diagram again. We're going to talk about it a little bit more. You were introduced to it in last video, but we're going to talk about a couple things. This time we're going to talk about endothermic processes. In other words, processes that take in heat, and we're also going to talk about exothermic processes. And exothermic processes are processes in which heat is released. So as we look at our phase diagram, as we go from a solid to a liquid, we know that as melting, and that does take heat in order to melt. Going from a liquid to a gas, what we know as evaporation, also takes heat or energy. And going from a solid to a gas, which is called sublimation, also takes energy or heat. Now if we look at the reverse, going from a gas to a solid is deposition, and it actually gives off energy. And if we go from a gas to a liquid, which is known as condensation, that also gives off energy. And if we go from a liquid to a solid, what we know as freezing, that also gives off energy and is exothermic. So as we look at this chart, we can look at it and say, oh, okay, if I'm heading to the right, then I'm putting in energy. If I'm heading to the left across the line, then I'm taking out energy. Hope that makes sense. Now sometimes evaporation is also called vaporization. Means the same thing. You're vaporizing something, evaporating it, making it a gas. So be careful with the wording. Remember also that I've marked here going across at 1 atmosphere. Remember that when I hit the freezing melting line, that point is called the normal freezing point. When I hit the boiling line, or the evaporation condensation line, that is known as my normal or standard boiling point. So when they talk about normal, all it means is it's at 1 atmosphere. Okay, just as a little last thing, this line right here is often called the melting point line. Whoops, there we go. Because it represents melting point until you get to the triple point down here. And this line right here, until you get to the triple point, is also known as the boiling point line. So it'll hopefully help you there. Okay, so one thing we need to talk about is vapor pressure. Vapor pressure happens when you have a closed system. Say on A here, I just put some water in a container and close the lid. So there's no vapor present. After some time, it becomes B, where I have a constant water level, and the area above the water level has a specific vapor pressure of water. Okay, this is known as equilibrium. It's reached equilibrium. In other words, the water coming out of solution into vapor and the water going from vapor into solution are equal. That's why I get a constant water level. It's reached an equilibrium. Now this equilibrium is dependent on temperature and how easily something goes into vapor or out of vapor. Now if it is non-polar, that means they're not attracted to each other, my vapor pressure, the amount of area up here in this area, how much can go into vapor, is much greater if it's non-polar. So my vapor pressure up here would be extremely high for nonpolar, but relatively low for polar. So we can look at that, and in your book on page 187, there's a table, and you can sort of compare back and forth the vapor pressures between nonpolar and polar. You can also see how temperature affects the vapor pressure of especially water there on table 6.5. So take a minute, look at those tables 6.4 and 6.5 on page 187 in your book, and then come on back. Okay, so if we look at boiling points, if I'm at sea level, and I try and boil water, at sea level, water boils at 100 degrees Celsius. But the higher I go, say into a mountain, the higher I go, the lower the boiling point becomes. So say at Mount Everest, which is what, about 20,000, 28 feet above sea level, my boiling point is only at 76.5 degrees Celsius. So if you've ever gone backpacking, you know this, that if you get up high enough in the mountains, you don't want to take any noodles, because what happens is the water doesn't get hot enough to cook the noodles. It just makes them soggy and nasty. So you never want to take noodles for high up unless they're already cooked and all you're doing is rehydrating them. So now, if I increase the pressure, what happens when I increase the pressure to the boiling point? Well, if I increase the pressure, what's happening? I'm actually putting more pressure pushing down onto this liquid. And when I'm doing that, I'm forcing those gas molecules to stay in the liquid. So what happens? If I increase the pressure, the boiling point also increases. So you got to keep these two separate. So if I increase the pressure, boiling point increases. If I increase the altitude or height from sea level, then my boiling point goes down. All right, try and keep those separate. So really quickly, cohesive forces are found more in solids and liquids. Those are potential energy. As that energy changes into particles moving, which is kinetic energy, we get gases. We get the disruptive forces becoming bigger than the cohesive forces that hold things together. And we get disruptive forces being big and kinetic energy being big, like in gases. Now, not all substances can be changed into liquids and gases. Some substances, when energy is added to it, the bonds actually break, causing decomposition instead. That's the main part that you need to know in these few sections. Make sure you look at the tables and sort of compare boiling points and what happens to the pressure and the elevation and that kind of thing. And be aware of that phase diagram and what's going on in it and how energy is being put in. It's endothermic, entering, and when energy is being released, it's exothermic, like it's exiting the system. All right, we'll see you in class.